So welcome. So here we are. This is physics and measurement, and basically we're going to talk about, or we talked about last time, some important skills, some units, prefixes, dimensional analysis, significant figures, and I think that's about as far as we got. Maybe we got to scientific notation, we'll see. So this is what I said was the important math things, and today we just had a quiz to do with prefixes, but you see there's a whole bunch of other things in there as well. And for the next quiz, we'll be not only including prefixes, because prefixes don't go away, but we'll also be adding things like geometrical shapes, like area of a circle, surface area of a sphere, other things that engineers commonly should know. So we'll include that in the next time round. For prefixes, we have a whole bunch of tables, and there is a logic to the tables. There's a little bit of just learning. So you just got to learn that pico means 10 to the minus 12, or nano means 10 to the minus 9, etc. You've got to learn that. But then when it comes to some of the confusing things, like for mass, it doesn't seem to work out. It's not, 1 picogram is not 10 to the minus 12 kilograms. And the issue is not with the prefix, it's that our SI unit is no longer the gram, it's the kilogram. So there's the logic behind it. So you learn your prefixes and you remember that bit of logic, and you can work it out. And then for length, area, and volume, a very common mistake is people will learn micro is 10 to the minus 6. And so they think 14 micrometers squared is 10 to the minus 6 meters squared, 14 times 10 to the minus 6. But it's squared. So it's 10 to the minus 6 and 10 to the minus 6, which is 10 to the minus 12. So if you see on these, it goes from minus 6 to minus 12 to minus 18, as we go from linear to volume, or plus 3 to plus 6 to plus 9. Again, there's a logic to it. So it's not like you've got to learn 72 individual things. You've got to learn a few things with a bit of logic attached. Very, very important. Then we talked about basically dimensional analysis, and I said there's two bits about dimensional analysis. There's like a fun bit and a not so fun bit, and the fun bit is actually really important from a physics point of view, and that is, as I change the linear dimension, that is, I change the height, change the width, change the depth. If I change the linear dimension, say I double the linear dimensions, then no matter what the shape of the object is, I 8 times the volume. But I only 4 times the surface area. I only 4 times the cross-sectional area. If it's an area, it's 4 times. If it's a volume, it's 8 times. If it depends on volume, like mass does, because it's mass times density times volume, then I 8 times the mass. I 8 times the weight, and so on. And so I can play these games about, if I have a potato that's twice as long, twice as high, twice as deep, there's 8 times as much potato there, because there's 8 times the volume. That takes 8 times the amount of energy. And yet, because I double the width, double the height, double the depth, I only have 4 times the surface area. So I got 8 times the energy needed, but only 4 times the surface area. And all the energy is going to come through the surface area. So it's going to take longer to cook that larger potato than you'd expect, because yeah, it's a bigger potato, but I've got the volume is outstripping the surface area. If I made it 100 times wider, 100 times higher, 10 times wider, 10 times higher, 10 times deeper, I'd have 1,000 times the volume, 1,000 times the need of energy, but only 100 times the surface area. So it would take 10 times longer to cook. So that's what the food industry knows. So the food industry knows that if I make skinny French fries, they'll cook quicker. Biology knows if my cell gets too big, it can't feed itself, so it divides into 2 cells. And Hollywood doesn't know that if I make a spider the size of a house, it will not be that much stronger compared with how much heavier it is. Because the strength is about area, because it's about the cross-section of your muscles. And your weight is about volume. So if I make you 10 times taller, 10 times deeper, 10 times wider, then you will be 1,000 times heavier, but only 100 times stronger. Won't work out. You'll have a problem. So kind of interesting. The other side of it is this, where you actually do some calculations, and we did this last time, but basically you put down the dimensions. Sometimes people put down units, and for the most part that's okay, but there are some confusions that take place, especially because not all units are base units. A Newton is not a base unit, it's made up of other things. So it's better to work in dimensions. And the dimensions, it's not an L, it's a L with a square around it. That tells you its dimensions. It's not a M, it's an M with a, it's like a brand. It's almost like, it's one thing. So write them down properly. And you can only leave them as a double decker. You can't leave them as a triple decker. So whatever you do, however you start off, you've got to end up with that. Most common mistake there is people think that the number should be included, but by definition, a number is dimensionless. Okay, so what's the use of this? The use of this is that, as we'll find out in a minute, the dimensions on the left-hand side of an equal sign have to equal the dimensions on the right-hand side of an equal sign. So if you tell me that something with dimensions of length over mass is given by, I'm going to make something up here. I'm going to make velocity, that would be length squared over time squared, that's velocity, times mass. I know that can't be true because they don't equal each other. So I know that equation is not right. You can put whatever number you like in front, some magic number. It's never going to make it right. So it is quite useful. It's just a little bit, it's not as interesting as spiders crawling over things. Then we started talking about basically significant figures because the problem is, in a nutshell, if I measure a distance traveled as 22 meters and I divide it by the time taken as 7 seconds, so I had 22 meters divided by 7 seconds, that gives me a speed of 3.142 ... It goes on forever. And the implication is I can tell the difference between 3.142 and 3.143 and 3.141, for example, if I stop there. If I had the next bit, it implies even higher precision. So I had a lousy measurement of length, because it's not 22.000 meters, it's 22 meters. And I have a lousy measurement of time because it's not 7.000 seconds, it's 7 seconds. I have a poor ruler, I have a poor time, and suddenly I have this really good, very precise speed. And it cannot possibly be. And so there's a whole idea about how do we write down measured values so that they make sense. And the trick is you've got to think in terms of columns. I noticed when I came to the States, the first time I came to the States, I was on an interstate, I was behind somebody, and somebody came up the outside and pulled in front, and somebody came up the inside and pulled in front, and they nearly hit each other. Okay, they were going. And in Britain, if you pulled up on the slow side, you would get a ticket so quick. Certainly when I was there, you would get a ticket. It was like you never overtake on the inside. And you always indicate when you're changing lanes. You never just veer to one side. And I came to the States, and it's a different culture, so people are veering all over the place, and it's like... And it's a bit like that with the math. You've got to learn, you think in columns. They mean something. So 72 is a different meaning from 72.0. And yet, even in computer programs, if you look at some of the computer programs, if you have, say, 69.1 and 27.3 and 28, it will put it down like that. Even in some computer programs, it puts it down like that. And the idea is, if it's measured with the same ruler, it has the same precision, and so it should be 28.0. So my advice is, even though you're going to use your calculators, get used to writing things down as best as you can in columns, and then keeping them, in columns, and being careful about, should I put a 0 at the end or not 0 at the end, because it makes a difference. So we say, when we write a number, we assume it has a certain uncertainty, and that depends on our measuring instrument. The last digit will be uncertain, it's a guesstimate, and the earlier digits should be counted. We count the number of millimeters. We guesstimate the amount of a millimeter that we're in between. That's provided that my ruler has millimeters on it. If my ruler only has centimeters, then I count the number of centimeters and I guesstimate the fraction of a centimeter in between. If my ruler only has decimeters, I count the number of decimeters and I guesstimate the fraction of a decimeter that my line is in between. And the rule is you can't guesstimate more than in tenths. So you can't say it's a quarter, that's 0.25. You can't do that. You've got to go in tenths. So 0.1, 0.2, 0.3, 0.0, 0.9, whatever you like. But you can't do better than that, even if I measured the ceiling tiles. If I wanted to know how big this room was in terms of ceiling tiles, and I could see that at the end it's not a whole ceiling tile. I'm not allowed to get a magnifying glass. I'm not allowed to get a ruler. I've got to use this as my measuring scale. I can divide that ceiling tile into tenths. No better than that. That's the rule. Because then I know, when you measured this, I know that your ruler was actually in tens of meters. It's a lousy ruler. I counted 2 tens, and then I guesstimated the 2. That's my guesstimated number. So when I write down 22, I mean I'm certain about the tens, I'm uncertain about the 2. We're allowed to differ on the 2. If I meant that my ruler was in meters, I should have written down 22.0 if I thought it ended exactly at 22. So the way you write the number down tells what kind of ruler you used. And that's a skill that we learn to deal with. So the first thing is, can we talk about this? And we say, yeah, we're going to talk about it in terms of significant digits. And let's work out how to determine the number of significant digits. And the basic rule is the left-hand most non-zero digit is always the most significant. And then if there is a decimal point, you took all the trouble to put that decimal point there. So you mean every column. So that 0 counts. Now down here I've got a decimal point, but I still take this as my most significant digit, and that's my least significant digit, and I count all the ones in between. So that's my most, that's my least, and I count all the ones in between. If there's not a decimal point, then these guys at the back are just placeholders. They're just to tell you, this is not 27, it's not 2700, it's 27, it's not 27, it's not 270, it's 2700. They're placeholders. So on this one, the 2 is my most significant, the 7 is my least significant. That's only got 2 significant digits. This 2,700 meters, what ruler did I use? Did I use a meter ruler to measure this value? Did I use a ruler that had tens of meters? Did I use a ruler that had hundreds of meters? Did I use the ruler that had thousands of meters as its smallest division? It's not going to be ones, because that would be 2,700 point something. And it's not going to be tens, because that would be 27. I don't know how I do that. I suppose I have to do that. That's not nice. It's not going to be that, because if I had a ruler that, well, anyway. It's got to be that that's the size of my smallest. Well, that's not tens, it's not units, it's not tens, it's not hundreds, that's thousands. So my ruler had 0, it had 1,000 meters, and it had 2,000 meters, and it had 3,000 meters, and my length of string was like that. So I said, I can count the first, I can count the second, I'm somewhere between the second and the third. I can guesstimate that. So it's 2 in the thousands, and then I reckon it was 7 hundreds. So by writing it down like that, as opposed to like that, I've changed my ruler completely. And I've got to match where I write numbers down to the ruler I use. Now, there's this thing called dividing or multiplying your way to precision. I give you that example of you have 22, which is a lousy distance measurement, and you have 7, which is a really bad. That means your clock went 0, and then the next beep happened at 10 seconds. It's a lousy stopwatch. It's like a miserable stopwatch. But if you try and work out your speed, you could put down numbers forever, implying more and more precision. You can't do that. So we have these rules about truncating in calculations. And basically what happens is if it's multiplication or division, you use the poorest number of significant digits. This is 3 and that's 2. So my answer must only have 2 significant digits. So it would be 26, not 25.83. And if I'm adding and subtracting, I used the poorest number of decimal places. And that's going to be 0 and 2, so my answer must have no decimal places. I can prove the first one to you by just simply using logic. So I'm going to go 2.1. Let's do long multiplication. So I go 2 3s are 6, 2 2s are 4, 2 1s are 2. I go 1 3 is 3, 1 2 is 2, 1 1 is 1. I add them up and I get 3 8 5. I get that, agreed? Now, that's, let me change color pen. Let's just do this. So that is an uncertain, you probably can't see that. Let me do it in black and then you can see it. That is an uncertain 3, and that's an uncertain 1. So a certain 2 by an uncertain 3 gives me an uncertain 6. A certain 2 by a certain 2 gives me a certain 4. So that's fine. For the 1s, an uncertain 1 multiplied by an uncertain 3 is a really uncertain 3. An uncertain 1 multiplied by a certain 2 is still uncertain because that uncertainty is in the 1. And an uncertain 1 multiplying into a certain 1 is still an uncertain answer of 1 because the first one was uncertain. So that means that that's uncertain, that's uncertain, that's uncertain, and I'm only allowed one uncertain digit. So the 2's safe, but I've got to summarize all these other things into one digit. The 8 takes the 5 to a 6. Oh, so the rule gives me 2 6. And logic gives me 2 6, so I'm comfortable with that. Learn the rule. You don't want to have to be doing this every time you do a problem. Just learn the rule. For multiplication, division, poorest number of significant digits. For addition, subtraction, poorest number of decimal places. Let's have a look. Factor label method. So factor label method was taught to me by my buddy, Mr. Nyan, who was the chemistry teacher at King High School, and it's a wonderful system. This says, convert 3 pecks per dross. Whoa, what on earth is that? So, when I was young and naive, I used to give people questions that had meters and seconds and centimeters and hours and inches and all that. And then after a while, one of my students pulled out their calculator and all the conversions were on the calculator. So it was like I wasn't testing anything. So I started using pecks and dross, basically. They're just, a peck is if you like a length, and dross is if you like a time. That's typically the way I do it. And I say, well, okay, you have 3 pecks per dross, so 3 peck. Here's a trick. Per dross means for each dross. So dross is on the bottom. It's a 1, yeah? Per dross means per 1. And I want to convert it into meters per second, but I need a conversion factor. So this is what you do. You say, I don't care where you begin. I don't want peck. I want to get rid of peck. The way you get rid of something that's on top is you write something on bottom. So the peck has to be underneath. And we all know we're going to use a conversion factor, so I find my conversion factor. 1 meter equals 6 pec. So I'm converting from pec to meters. If pec is on the bottom to cause cancellation, my meters have to go on top. And I go, well, what is it? Oh, 1 meter is equal to 6 pec. I got rid of my pec. And now I go, okay, I don't want dross. Well, dross is on the bottom. I want to cancel it out, so I've got to put dross on top. And, well, I want to convert this into a time in seconds. So I want seconds. The only place for the seconds to go is on the bottom. And 1 dross is equal to 5 seconds. And again, that goes like that. So this equals 3 times 1 times 1 is 3 over 1 times 6 times 5 is 30. 3 over 30, which equals 0.1 meters per second. So it's there. So that's the skill. I'm your coach. If you lay it out like this, you will get it right more often than not. If you do it in your head, you're going to get it wrong, especially when you're nervous. You won't get it wrong in homework. You're not nervous at homework. But in a test, you'll be anxious. Your chances of getting it wrong increase quite significantly. So my advice is, you know, I'm like telling you, your backhand is a little bit loose. Tighten your grip. I'm kind of saying that here now. You know, you're the player. You've got to decide. But my advice to you is just learn this method. It works really well. I taught chemistry for a year in high school, which was ironic because I kind of failed chemistry. So it's like, in Britain I didn't need it, but I failed it. I passed it. I didn't pass the lab. I had a disaster of a lab day. So it was just one of those days and everything went wrong. I flushed down all my crystals before I masked them. It was a disaster. And so I got a pass with an asterisk on it saying, you know, you failed the lab. So, and then I'm teaching it. And it's like, oh my word. I dreaded teaching it. I was doing it for 1 year until they could hire a chemistry teacher. And I was spending all my time on this stuff and anxious about it completely. And what I found was that I could kind of grade the papers in terms of, you know, who did well and who did poorly just by looking at the papers. Because the people, for the most part, who wrote down all the steps got the answer right more often. So you could almost just glance through them and say, oh, they've got a method here. They're going to do okay. And the other people, number here, number there, a little bit of an equation here. It was, as often as not right. So monitor yourselves. You should try to write complete answers. And if you can't, that's an issue. That says that your thinking's not clear. It's not that you're just truculently refusing for the most part. If people can write a clear answer, they're happy to do so for the most part. So if you can't write a complete answer, it's probably because your thinking's not stepwise, it's not clear. And secondly, if you do make a mistake, it's basically impossible for me to find. So a complete mistake. Whereas if you write things down bit by bit and you use layouts, it will affect your performance. It's like form. It's learning to run properly. Form is important. So this is, actually I missed one bit. Okay, it doesn't matter. So this is like my kind of, again, coaching tip for you. So read the problem and try and visualize the situation. I'm not just words, that's really important. If you don't have, then draw a diagram. If you don't have you don't have to be an artist, but you'll get better. You will get better as you practice. People do little diagrams with little arrows and they're useless. You need little squares and big arrows, a nice big diagram. If you're doing angles, a reasonably precise angle. Make 30 degrees look like 30 degrees. If you do everything at 45, it's the worst of all worlds. If it's supposed to be 30, I have a little angle and a big angle. So when I'm propagating angles around my diagram, it'll go little big, little big, little big. It'll work its way around. If I draw what should be 30 degrees as 45, then I don't have a little and a big angle. I have two angles that are the same. And it's very easy to then get confused about what the angle is. If you make a mistake, it's not obvious. Man, I'm saying that that's 60 degrees, and yet it don't look like 60 degrees. Well, yeah, if it's 45, it's all going to look like 45. You never get anything out of that. So really, especially at the beginning, really slow down a bit on your diagrams. And so how many people got a protractor? Good. Use a protractor. Just take the time. You don't need it in the end. Your diagrams will be really good in the end if you practice to begin with using a protractor. If you never use a protractor, if you're always 45 degrees, they're never going to improve. So it's really important. These little things really matter. It really makes a difference. So draw a diagram. If you can't draw a diagram, then why can't you draw a diagram? That's the issue. List the parameters. Eventually, most people stop doing this. Whenever I feel uncomfortable, I do it. Because what it does is by saying mass equals, time equals, distance equals, by saying those things, I'm jogging my memory and I'm sorting out what I know and what I don't know. And don't forget to put down, so kinetic energy equals, I don't know. Put down what you're looking for as well as what you know. And it will really help you. Eventually, you get to the stage, I know how to do this. And for the most part, you can leave it to one side. But whenever I feel uncomfortable, I'm back doing my list because it's going to help me. Note the unknown. I once spent a few minutes not able to do a problem because I didn't put down the unknown, and it was a bit of a lesson. And then you choose an equation. You choose an equation from your library of equations. And these guys will pretty well tell you what equation to use. I will put in red herrings, like I might tell you the temperature. Nothing to do with this at all. It's just there so that, you know, it's not just blindly obvious from what I put down. There's only one equation which has F, M, and A in it, so duh. You don't even have to know what those things mean. So it's just to make it a bit less of a plug and chug. Solve the equation. Put numbers in. Get me a number. And then the thing at the end, does that make any sense? I can't tell you how many times people put down, they'll put 40 divided by a quarter equals 10. And there's no way that's true. Okay? When you think about it, 40 divided by something that's less than 1 must be more than 1. And yet people will just make that slip and they're gone and they're on to the next question and they're not thinking, does this make sense? This is not a math course. It's a physics course. So it should, although I will use simple numbers, which sometimes do mess up our intuition a bit because they're not realistic numbers, making a trade-off there. But, you know, you should check through and say, is this kind of making sense to me? And if you follow that, your score will improve. If you focus on that bit, or maybe that bit, then you'll often do the correct math on the wrong problem. And it's like, it's still wrong. It's like, you know, good math is required but not sufficient. So I mean that from the heart. Really do focus on that. Really try. So my colleague's little boy is a junior Olympian. This kid, he was 2, and I remember him running across this field when he was 2, and I remember saying to my wife, man, he can run. That kid can run. It was the most beautiful thing to watch. It was like, you know, my daughter's there like the rest of our family, kind of like vaguely. My mom used to run. Her legs used to go like crazy, but she made no forward motion. It was all like, my daughter's the same. It's just like my mom, running like crazy and not leaning forward, not going forward. And working like crazy to go nowhere. And I think it's quite sweet, but the Olympics don't like it. So this kid's amazing. And I saw then for me, the bit is the parents are like, you know, obsessed by his performance. This kid is, I bet every time he's run, they've written down his time. And I just think the pressure on a 10-year-old is like, you know, horrendous. But that's the way it is, you know. And they praise him tremendously when he does well, and he goes on from strength to strength. And I noticed his dad would give blow by blow of, you know, this is the meet we had, and this is what happened. This tall kid nearly passed him, but then my son came back, and, you know, clearly was very involved in it. And what he talks about is form. He says something happened, you know, this kid nudged him or kid ran past him, and he'll talk about how Kieran, his son, will lose form, and that's the end of it. When he stops running with grace, he slows down tremendously, because the better he runs, the faster he goes. And I never connected that in my mind. I'm not a sports person. It's like, I played cricket years ago with my brother. But it's like the faster he runs, because he's running better. He's keeping to the form. And I think it's a bit like that with these problems. It's like if you stay with the form, you will do better. If you don't have the form, if you're intuiting it in your head, then you'll make more slips, but also the work won't unfold, so you won't get to know what's the next step. They're all kind of in here jumbling around, when if you look at my stuff, it's all on the paper going step by step. And I'm not doing it that way to teach you. I just let you look over my shoulder. When I'm rushed, when I write my test down, sometimes I rush. I jump steps. I make mistakes. So my advice is just, especially in these first days, just take your time a little bit and go on from there. Let's stop there.